Hello, welcome to the webinar Wednesday. On behalf of the Powder Coating Institute, thank you for joining us for today's webinar on pretreatment and powder, how to improve your corrosion performance, presented by Ryan Tadich and Matt Rush of PPG Industrial Coatings. Before we get started, I would like to remind everyone that all attendees are on mute, so if you have any questions along the way, please type them in the questions panel. The speakers will address the questions at the end of the webinar. If we run out of time, there will be a contact information on the closing slide if you have additional questions. This webinar is being recorded and will be available through the PCI store within 2 business days. All attendees will receive a brief survey after the webinar. Please take a few moments to reply. We appreciate your feedback as PCI continues to develop new programs to offer the topics and training you need. Now I'd like to introduce the presenters for today's webinar. Matt Tadich started in the powder coating industry in 1997 and has since held several commercial and commercial management roles. He is currently a business development manager with the industrial coatings business of PPG, focusing on the growth in the powder coating segment. Ryan is a senior development chemist for the industrial coatings substrate protection segment of PPG. He has started working there in 2014 as a development chemist and has been serving and troubleshooting customer pretreatment lines for the past 7 years. He has also worked on developing and modifying new and existing products. Ryan has received both a bachelor's degree in chemistry from Duquesne University and a forensic science degree from Seton Hill University. Thank you for both here today. I'd like now to turn it over to Matt, who will begin today's webinar.
All right, so good morning to everybody. Appreciate everybody joining. We're having a little bit of a technical issue with Ryan's computer, so I'm going to control the slide. He is on the phone and will be able to speak to the slides. But real quick, because it's a lot of information in a fairly short amount of time. We're going to talk about start out talking about pretreatment, different substrates. Types of fabrication lubricants you may run into, and then different options for pretreatment, and then go into the process a little bit. Then we're going to talk about powder options, direct to metal, primer, some thermoplastic information, and then finally testing methodologies and different ways to just make sure that you and your customers are kind of talking the same language as far as performance and the testing criteria. So I will hand it over to Ryan. Ryan, just let me know when you want me to switch the slide. I'm on slide 4 right now.
Oh, thanks, Matt. Good morning, everybody. Today, I'm going to talk about surface preparation and pretreatment and its importance to corrosion performance. If you talk to anybody who's been in the paint industry for a very long time, they're all going to tell you that surface preparation is key to getting the best coating application and performance. Did you say you're on slide 4, Matt?
Sorry, yeah, slide 4, why we pretreat.
Okay, so I guess before we get into the specifics and get into the presentation, I'd like to take a minute to tell you about just the general purpose of pretreatment. It's the, I guess, Reader's Digest version is it's a crystalline layer that provides extra protection against corrosion. How does it do that? It enhances paint adhesion by providing more surface area. More surface area means you can apply more paint. Applying more paint means increased general surface corrosion protection. Another key thing that pretreatment does is it reduces underfilm delamination. So underfilm delamination occurs when you get a scratch on your part down to the bare metal surface, which creates your starting corrosion site. And what will happen is rust will actually spread underneath your paint to the point where you can actually just peel the paint off with your hands. That's essentially what underfilm delamination is. You can go to the next slide. So I'm going to talk about the total system approach, which actually doesn't start at the beginning of your production line. It actually starts at the substrate or parts that are coming into your door, whether it's a metal coil and you press your own parts, or you have a part supplier who presses everything for you and you just get the parts as is. So we'll we'll move on from the different types of substrates to all the different types of lubes that you might encounter and then how to remove them. And then we'll wrap up with touching on the different pretreatment chemistries there are. So let's you can go to the next slide. So we'll start with substrates, and then you can go to the next slide. So this is a list of the most common metal substrates you're going to encounter in the field. Carbon steels encompass your hot rolled steel and your cold rolled steel. It's the most popular substrate there is right now because it's easy to make and it's the cheapest one on the list here. The majority of lines out there usually run 60% or more carbon steel. Galvanized steel is becoming more and more popular because it has a zinc layer over top of your carbon steel, which acts as an extra layer of protection against red rust and is basically a sacrificial layer when it comes to corrosion. The aluminum and magnesium are actually becoming more and more popular because of their being lightweight metals. So in the automotive industry, you're seeing a lot more aluminum and magnesium parts due to people wanting to maximize gas mileage. Castings aren't as common, but one of the things I want to address about castings, in case anybody does run castings on their line, is that during the casting process, you can get pockets of gas entrapped into your casting, and they normally don't get a chance to escape those pores until they get into your curing oven. And by that point in time, you have a paint layer over top of it, which those gases escaping will create a defect called pinholing and will basically cause your part to fail QC. So the best way to address that issue is preheating your parts prior to going into your system, so that way you allow those gases to escape and you can avoid that defect. Lastly, I wanted to point out stainless steel is a passivated metal, which is why we use those to construct production tanks. So due to it being passivated, you can't pretreat it. You can go to the next slide. So this slide here is a cross-section of two different types of galvanized metal. There's electrogalvanized and hot dipped. Regardless of the method of the zinc being applied, there's a defect that is common to galvanized called nubbing, which is a defect that happens when you're applying the zinc layer where little pockets, there are little pockets or holes in the zinc coating surface that leave steel exposed, and when you actually pre-treat them, it comes out looking like little white bumps on the surface of your part. And if you end up painting over those, then you're going to have those, that you're still going to be able to see those bumps on the surface of your part. So the way to address that is by adding a complex fluoride to your system, especially a zinc phosphate. But we'll touch on that a little more as we get into the pretreatment section. You can go to the next slide. So now we're going to talk about what's on your parts, the different types of lubricants that you're going to encounter, and move on from there. So you can go to the next slide. So with the different types of lubricants listed here, the most common one you're going to encounter is drawing compounds. Mill oils are usually just on steel coil stock. They're typically very easy to clean off. If you happen to have anything that's hot rolled steel, pickled and oiled, that's something that's probably going to have a rust preventative on it. We'll go into the specifics of drawing compounds on the next slide, but I do want to touch on a couple other lubricants you might encounter depending on what kind of parts you see. Heat treatment oils are very common in the fastener industry. So if you treat any type of fasteners or anything, that you might encounter some heat treatment oils. Those are typically usually pretty easy to clean off as well. And then if you deal with any type of wire, or I know there's some places that use wire to make like hood props and things like that. Those wires are typically lubricated in a stearate, and stearates can cause an issue in your system by causing a lot of foaming in your cleaner and rinse stage. but we'll talk about that a little more on the next slide. So this slide here, we're going to talk about the different types of drawing compounds. Drawing compounds are essentially designed to alleviate friction in a press room. So if you're pressing a really difficult part, something with a really big deep draw, for instance, a bathtub or a sink or anything like that, the amount of stress that metal is going to undergo in a press operation is going to be a lot, considering how deep the draw is. So what drawing compounds do is it tries to alleviate that stress so the metal doesn't actually break. The most common drawing compound you're going to see is straight petroleum oils. They're typically very easy to clean off. Very rarely do we see difficulties in the field dealing with just straight petroleum oils. We do run into a little bit of a problem whenever you have a straight petroleum oil that has additives or pigments in it that are designed to help even more with a deeper press. So sometimes those additives and pigments can be very difficult to clean off. So that's where you run into a little bit of trouble. Another very popular drawing compound is an emulsion, and what an emulsion is it's a straight oil with a compound in it called an emulsifier, which allows it to be mixed with water. So you can actually dilute the oil using water, and it will actually mix together as one solution. If you look at the picture on the left of the slide here, that's actually a side-by-side picture of a straight oil on the left and an emulsion on the right. The emulsion kind of looks like milk. And again, with the additives and pigments, that's where you can run into issues with cleaning. Synthetic lubricants are becoming more popular due to them being a lot more environmentally friendly than straight petroleum oils. The synthetic lubricants, though, since they don't have any petroleum in them, have to have extra corrosion inhibitors built into them to make them as robust as a straight petroleum oil. And then soaps, like I mentioned before, the stearates are soaps. They generally are a dry film versus the rest of these listed here are liquids. They typically are a dry film, and like I said, they will cause a lot of issues with foaming in your stage if you don't have the correct cleaner. You can go to the next slide. Some of the incompatibilities you could run into in relation to lubricants is some of the extreme pressure additives. If you don't maintain your metal stock properly, if it sits for too long, can actually do the opposite of protecting your metal and aggressively attack your substrate, so where it will rust. The picture on the left is actually a panel we use in an in-house training class that we use as an example, and it's been sitting out in the lab for years now. Other storage problems are something that we call varnishing, which is if a lubricant's sitting on a shelf for too long, it begins to lose its properties. It starts to get really, really thick and heavy, and it's pretty much impossible to clean off. So it's basically like a varnish. And the best way to maintain and avoid these first two problems here is first in, first out. Simple as that. Some of the pigments that were mentioned on the previous slide, like mica and calcium carbonate, can also be a little difficult to clean. And lastly, and this is probably one of the most important ones, is don't mix a synthetic lubricant with a straight lubricant. You might have a good synthetic lubricant and a good straight oil, and you might think, oh, well, let's put them together and make it great. Well, what you're going to end up with is something similar to a varnish, and you're going to pretty much have to dispose of all of those parts. So to touch on a couple final points about drawing compounds is the type of lubricant you choose is very important, and you're going to hear me mention this several times as this presentation moves forward, is that the type of lubricant you choose and the cleaner that you have online is like a marriage. If you don't have total compatibility, it's not going to work. So make sure that you have the right lubricant and the right cleaner. We were mentioning emulsions before being able to cut with water. So if you have an emulsion that, is supposed to be 2-to-1 and you dilute it to 3-to-1, you can end up running into, quality issues there where, you might end up with some small rust spots on your parts. Application is the last one, and it's one of those too little, you end up with rust spots, and too much, you might not be able to clean it all off in the time you've allotted in your cleaner stage. So I've been at a customer before where they had so much lubricant on a part that they actually had to put spill pads down on the floor from the loading area to the first stage on their production line because of how much oil was dripping off the part. So they ran into cleaning issues, surprisingly. Next slide, please. So now we're going to transition over to surface prep, and we're going to talk about how to remove all these soils. Next slide, please. So for surface preparation, there's 2 ways to go about getting a good clean surface in order to apply a good pretreatment coating. The first being mechanical cleaning. So that's, your shot blasting, your sandblasting, where you're shooting some type of media at the surface of the part at a very high velocity in order to remove the soil or the defects. It's a great thing to use. We highly recommend it, but it doesn't fit everybody's budget. So another way to go about it, and what we're going to focus on, is chemical cleaning, which is going to be removing all these soils through a chemical reaction. Next slide, please. So these are different types of cleaning chemistries. Solvents aren't common on a production line. They're typically used as a pre-wipe if you have a difficult lubricant that you can't clean, or if you have something very heavy like a grease. Solvents are usually pre-wiped before going into the production line in order to try to give your cleaner a leg up in removing that. The alkaline cleaner stage is the workhorse of a production line. It's going to remove, all the lubes we talked about on the previous slides, all the rust preventatives we talked about, and any dirt or dust or anything that might get on the surface of your part, just sitting in the warehouse and whatnot. Pretty much anything that is organic that is on the surface of your part will be removed in the alkaline stage. Now, there's inorganic components that can also be on the surface of your part, like scale and carbon smut, which are byproducts of the milling process. So you will need an acid descaler or acid pickle. I will use those terms interchangeably. Next slide, please. So this slide here is just a visual of, how cleaning would work. So that yellow layer that you see on the top there is your oil. So when you go through your alkaline stage, that's going to be removed. And maybe that speck of dirt in the middle will be removed, but the rust and the other dirt will remain because it's inorganic. So you want to make sure that if you have inorganic things on your surface that you're going to use an acid pickle. Next slide, please. So how can you tell if a part is clean? Basically, you look at the first rinse after your cleaner. So as the parts are coming out of that rinse stage, you want to look and see if you have what we call water break, which is what you see on that picture on the left, where water beads up immediately and doesn't sheet off in a uniform way like the panel on the right, which is a water break free one. Some of the causes of water break is high oil content. That's going to come probably naturally as you process square footage, because your oil is going to remain in your cleaner the entire time, even if you're pumping in fresh cleaner. So once you hit about 2 or 3% oil content in your cleaner stage, it's either dump and recharge or do a partial decant depending on your tank size. The cleaners are designed to run at a specific temperature and concentration range. So if you're out of spec on the low end, the surfactant package that are in those cleaners isn't going to work, and you could potentially see foaming being out of the temperature range. Another very common one is somebody switching lubricants in the press room and not informing the production line. That goes hand in hand with the wrong cleaner, which, like I said before, if you don't have the right cleaner and the right lubricant, it's not going to work. You're going to see water break. Sometimes you might be running more square footage and end up with a shorter contact time than you initially planned due to increasing line speed. So if you drop from 90 seconds to 60 seconds, yeah, you might see a performance change in your cleaner due to that. And then low spray pressure based on, routine maintenance, making sure your nozzles are clean and things like that. If you can't get the chemistry to the part, how are you going to get it clean? Next slide, please. So this is a list of some of the different inorganic soils that we're going to talk about removing with an acid pickle. So we already talked about scale and smut, but some of the more common ones that we see nowadays are laser oxides on the edges of parts from cutting tools, as well as weld scale. And then you might run into a part that sat for a little while and has some rust spots on it. Those can all be removed with an acid pickle. Next slide, please. So this is a list of the different types of acid pickles that are very common. Hydrochloric acid, while very cheap, typically isn't really seen in the field a lot because it has a problem with generating a lot of fumes. And so from a safety standpoint, we don't normally see it online anywhere because of the fuming. Most places will opt for sulfuric acid or phosphoric acid. Depending on what they're trying to do. Depending on what they're trying to do, one of them will fit better than the other. There are some phosphoric acid blends out there, including one that is a sulfuric phosphoric combination. But usually, you'll opt for one or the other. They usually perform better alone than together. Organic acid blends are a very specific product for specific types of things. Most places opt not to use them because they're much more expensive than the other three acids listed here. One of the things I want to mention with the non-inhibited being in parentheses there is that there are products out there that are inhibited acids that are designed to clean production tanks. And if you don't clean those production tanks properly or properly rinse them after you use an inhibited acid, if you end up with an inhibited acid cross-contaminating into your pretreatment stage, it's going to kill your pretreatment and you're going to have to dump and recharge that tank. Next slide, please. So acid pickles are mainly used on lines now to clean up weld areas here. So, I'm going to give you, the terms on the slide here. The face area is away from the weld. So it's going to look like a standard area or basically a standard surface of like a part that's not welded. So that's going to look like your standard pretreated area no matter what. Your weld area itself will have a lot of weld scale and oxides and possibly silica inclusions depending on the welding material. The silica inclusions can be very, very difficult to remove, and sulfuric acid actually does a tremendous job of removing silica inclusions. So we typically recommend sulfuric acid unless you're using a spray system, then we recommend phosphoric acid. The heat affected zone is also an area that is contained with oxides, and sometimes there's weld spatter in there, so you want to try to remove all of that in order to get a smooth surface. With an acid pickle, you can actually get the heat affected zone to look like a face area, but if you look under the weld area and under a microscope compared to the face area, they're not going to look the same, and it doesn't matter how good the acid pickle is, they just won't look the same due to the nature of the welding. One other thing I want to mention about acid descalers is that their efficiency is contingent off of iron content. So the higher the iron content, the less efficient your bath is going to be. So if you have a high iron content acid descaler, you're going to end up with a weld area and a heat affected zone that has a very poor pretreatment coating. Next slide, please. So after your acid descaler, we highly recommend using a neutralizing rinse over a regular city water rinse with a high overflow, because a neutralizing rinse is an alkaline material that does a much better job at neutralizing acid residues. We typically recommend a city water rinse after the neutralizing rinse, but if you don't have the space for that, and you're going directly into pretreatment, maintain the pH between 5 and 8 for an iron phosphate, a heavy zinc phosphate, or zirconium, and a pH of 8 to 9 for the rinse conditioner on a zinc phosphate line. Next slide, please. So now we're going to talk about the different pretreatment technologies. Next slide. So iron phosphate is the oldest pretreatment technology there is. It's also the cheapest. So it's still very popular, even though from a corrosion performance perspective, it is not as robust as zirconium or zinc phosphate is. However, it still does a very good job as far as hitting specs that are for parts that might not see the elements, something like a filing cabinet or a vent cover that's in your house. Chances are that probably is coated with an iron phosphate because it's not being exposed to the elements. So you can still get good performance, just not when it comes to really extreme conditions. Another thing I want to point out with iron phosphates is that there actually isn't iron in an iron phosphate product. That comes from the steel itself. So with that being said, you can't apply an iron phosphate coating to a galvanized part or an aluminum part for that matter. What you end up doing is you just end up etching the surface so you can get a little bit more surface area for your paint to stick. Cleaner coaters, most cleaner coaters are iron phosphates. There are zirconium cleaner coaters out there, but not many. They're still really under development. Cleaner coaters do both cleaning and coating in the same stage, so you run the risk of having an issue where you might be cleaning more than you're coating, which could affect your corrosion performance because your coating weight might not be high enough in order to get the performance you need. Zirconium is the newest of the pretreatment technologies. It's actually considered a nanotechnology because of how small their crystal size is. So it provides excellent coverage. It's actually becoming more and more popular for customers to convert to this product because it is the most wastewater friendly, it generates the least amount of sludge, and you can operate it at room temperature. And as well as it will apply a pretreatment coating to everything with the exception of stainless steel. From a corrosion perspective, zirconium is close to zinc phosphate, but not quite as good as zinc phosphate, depending on the spec. Usually, with most customer specs, it will be able to match zinc phosphate, but if you have something that's a really challenging spec, then zinc phosphate will probably still outperform it by a little bit, but they're still very close. With that being said, your best corrosion protection from a pretreatment perspective is a zinc phosphate with a sealer. Zinc phosphate lines are usually anywhere between 6 or more stages, so they require a lot of square footage in order to run a zinc phosphate line. One of the most important things about a zinc phosphate system, though, is that you need a grain refiner stage before the zinc phosphate itself. Otherwise, you will lose the tremendous corrosion protection it provides because the crystals will be a lot bigger and will be a lot more brittle. So you can see a lot of adhesion loss, and there might be certain spots where you don't have a coating, and that will completely affect your corrosion performance. So you want to make sure that your grain refining rinse is running at an optimal level. Next slide, please. So after you pre-treat your part, there's still inorganic salts on the surface, and once you get out of a zinc phosphate stage, for example, those usually operate at 125 degrees. So the combination of the rinse will get rid of those inorganic salts as well as stop a zinc phosphate reaction from still going because it operates at a certain temperature, and the rinse will drop that temperature and stop the reaction where it's at. Next slide, please. So we're gonna touch on final seals here. Next slide. So your final sealer is going to continue to remove the inorganic salts that are on the surface and then it's going to basically seal the holes between the phosphate crystals. But the example that I like to use for this is if you remember, middle school science class, the teacher takes out a jar and fills it with marbles and then asks you if you think it's full and then proceeds to fill it with sand to prove to you that it wasn't full. So think of your phosphate crystals as the marbles and your sealer as the sand to give you an idea of how it actually interacts with each other. Now, the sealer will improve corrosion performance because it's filling in those gaps, as well as enhance adhesion and reduce the tendency to blister. As far as corrosion performance goes, using a sealer is going to boost the performance of any pretreatment that you use, with the exception of zirconium. Zirconium doesn't require a sealer. But with an iron phosphate, with or without a sealer, you're going to see a big difference between with sealer versus without a sealer. With zinc phosphate, the gap's a little bit closer. Next slide, please. So for your final stage, we highly recommend, even though with powder you don't necessarily need a DI or RO rinse, but we highly recommend a DI or RO rinse because it's the cleanest water you can have, and it will give you the cleanest surface to be rid of the inorganic salts and everything that are on there. It'll give you the cleanest surface before you move on to your paint system to give you the best paint adhesion you can get out there. The inorganic salts can kind of interfere with paint adhesion, so the DI or RO rinse is the best rinse you can have. So we strongly recommend that. Even at the bare minimum, if you don't want to dedicate a whole tank to it, we'd recommend at least putting a DI halo that backflows into that rinse stage. So that concludes the pretreatment segment, and I'll hand it back over to Matt.
Excellent. Okay, thanks, Ryan. Appreciate that. Okay, so now we're going to talk a little bit about our options for coating. Now that we have a properly pre-treated. Sorry, did the screen go off? I had it flicker here.
You're good.
Okay, all right. Sorry about that. So now we have a properly cleaned part. Talk a little bit about the powder options. We'll look at different chemistries and what our expectations should be for performance on those, and a couple different systems of powder. So when you look at the different chemistries, kind of your off-the-shelf products that you can get from your powder vendor, your TGICs, TGIC-free coatings, urethanes, polyester epoxy hybrids, you're gonna look somewhere between 500 hours to 2,000 hours if you have a kind of an optimal substrate to apply to. Your acrylic epoxy hybrids will give you a little better performance in about 1,000 to 3,000 hours. And then the epoxy coatings will kind of give you your best option at 2,000 to 5,000 hours on properly pre-treated substrate. Now there's ways for your powder supplier to engineer coatings to give you better performance. Probably the most important thing they could do to engineer a product would be to improve the edge coverage. So inherently, powder is going to want to run away from any edge. The higher the flow, the higher the gloss, the more it's going to run away. But every coating is going to want to kind of run away from that edge. So if you look at the cross section on the screen on the left, it's just a standard coating, and you're able to build about 4 microns, or about, I think it's a little less than 0.2 of a mil. But with the products engineered specifically for edge coverage, we can improve that by about 9 times, up to 37 microns, or about 1.5 mil. So obviously, in a highly corrosive environment, the product on the right side, it will perform better. The other option, or another option, is a 2-layer system. So we can put down a primer and then put down a top coat. Obviously, just by the fact that you're improving or increasing the film build both on the part and on the edges is going to improve your corrosion performance. If you use an epoxy primer, you can get kind of because of its cross-linking properties and wetting properties, you're going to get a better adhesion to the substrate. which will help minimize corrosion getting underneath the coating and causing delamination. Also, just again, by the fact that you have more coating on the part, you're less the probability of gouging to the substrate is decreased. So obviously there's different primers you can look at, and there's different primers that can be formulated to have better corrosion protection. Probably the most common of that is zinc primers. As you may be aware that zinc has sacrificial properties. The corrosion will attack the zinc before the substrate, prolonging the life of that substrate. We generally will recommend a shot blast preparation on the substrate. That'll give you your best results. And in that situation, we can see 5,000 hours plus of salt spray protection. The downside of that is zinc primers have extremely high specific gravity. If you've ever worked with them before, you probably know they kind of spray like sand, and the coverage on these coatings is not very good. So it will add some cost to the process and material cost. But standard epoxy primers also can do an excellent job of protecting the substrate. Chemical or mechanical surface prep, and you're looking more at 3,000 to 5,000 hour window of corrosion protection. The lower specific gravity will mean a lower applied cost, so it is a lower cost option than the zinc primers. The other thing I want to note is that if your top coat, well, let me say this: if your part is going to be exposed to UV, if it's going to be outside, where it's exposed to UV rays, you want to make sure your top coat is, if you're using an epoxy primer, you want to make sure your top coat is UV absorbent, and your powder supplier can tell you. If it is not a UV absorbing top coat, if it's a UV transparent top coat, meaning it may be a weatherable coating, it won't deteriorate in the UV rays, but it also isn't stopping those UV rays from getting to the primer layer. If that's the case, you need to make sure you use a weatherable primer. Otherwise, that primer will chalk and cause delamination. So if you're not sure, check with your powder supplier, and they'll be able to let you know if an epoxy primer will work or if you do need a weatherable primer. Finally, another viable option, actually a really good option for corrosion protection, is thermoplastic coatings. And everything we've talked about to this point have been thermoset coatings. And if you're not familiar with the difference, a thermoset coating, when it is exposed to heat, when it goes in the oven, will melt and flow, cross-link, and cure. And there's a chemical reaction that takes place. Once that happens, that coating will not revert back to its original state. So you think of an egg, you crack the egg and you fry it up. There's nothing you can do to return that to its original form once that chemical reaction takes place. Thermoplastics, on the other hand, they melt and they flow, but they don't cure. So they will reflow when they see their melting point, similar to water and ice cube. You can go back and forth between the solid and liquid state based on the temperature that it's exposed to. Thermoplastic coatings react the same way. They tend to be high film build coatings, which is why they, part of the reason why they provide such great corrosion resistance, anywhere up to 100 plus mils. But you're completely encapsulating the part, creating an exceptional water barrier. Now, these coatings tend to be very flexible, very impact resistant, but they're not particularly hard coatings. So they will gouge, and if they do, if they are breached down to the substrate, corrosion will tend to run more quickly once it's under, because they don't have the adhesion properties of thermosets. On the plus side, they are field repairable. So if a breach of the coating is recognized quickly, it can be repaired in the field. If it's small, you can reheat the coating and it'll flow back into it. If it's a larger defect, you can sprinkle some powder or some. Sometimes there are bands of material you can put on it and reheat it and have them flow into the defect. And so that is an advantage over thermosets. They're not for high temperature applications. Nylons tend to soften around 350 Fahrenheit. Polyolefin, polyethylene coatings about 220 degrees. So they're not high temperature coatings. But in the right application, for example, buried pipes or tanks, something where you can encapsulate the part and reduce the risk that coating is going to be breached, they are an excellent alternative or option, I should say. I want to talk a little bit about the testing methodologies that we look at, and to make sure when you look at performance specifications, you're kind of looking at apples to apples, and everybody's talking the same language. Salt spray and it has been the kind of the traditional method of testing, and usually is evaluated, traditionally has been evaluated as this creep from the scribe, a line cut down to the substrate or an X, and then measuring the scribe from that. As manufacturing processes have evolved, we see more sharp edges. We're seeing more requests for, again, coatings that will provide a better edge coverage protection. And it's important to understand that you can engineer coatings to do one or the other, or maybe somewhere in between. The white panel, which I think was 2,500 hours, you can see from the scribe, looks very good. Very little creep, if any, from the scribe, but there is significant corrosion on the edge of that panel. Whereas the blue panels, the edges look good, but there is significant creep away from the scribe. So it's important to understand what you're trying to achieve, and then communicate that to your power supplier to make sure they give you a product that will work for your needs. The other thing that is the type of testing that is we're seeing more and more over the cyclic testing. Traditional salt spray testing is a 5% salt solution at 95 degrees Fahrenheit, and it's a continuous mist. Except for the hour or so, or the lab tech is checking parts or adding parts. It's a continuous process. Where the cyclic test, and I just took one. There's multiple tests out there, but the GM 9540P. It's a 120 degrees Fahrenheit intermittent fog humidity for 8 hours, salt fog at 75 degrees Fahrenheit for 8 hours, and then a dry period at 140. And the idea is that's more real world, that where you go through these cycles of moisture and heat and dry, and where the salt spray is just a consistent misting that takes place. Now, salt spray is an excellent comparative test. If you have I know I perform to a certain level with this coating or this system, and you're testing a new system, it'll tell you if you're better or worse than that. Whereas cyclic, in theory, is more real world, and you can try and associate, performance, actual performance in the field to those tests. The other thing we're seeing more of that you should be aware of if you see it come into your shop with a specification of ISO 12944. And that is 5 classifications, C1 through C5, with different levels of corrosion environment. And then within those 5, there's low, medium, high, and very high. So if you see that communicated, again, you have a spec come in that says I need ISO 12944 C3 medium. You can communicate that to your coating supplier, pretreatment supplier, and they should be able to recommend products that will meet that, or give you the best opportunity to meet those requirements. And within each of these criteria, there are, the lower end tend to be, salt spray requirements, non-cyclic, and then as you get into the higher end of cyclic testing. But your coating supplier should understand what tests are required and for each level, and can direct you in the right direction with that. Generally, C1 through 3 are direct to metal, C4 and 5 are a primer top coat system. And then again, as you're communicating performance, you want to make sure everybody's talking the same language. So somebody says, hey, I need 1,000 hours of corrosion protection. Okay, is that salt spray, humidity? Is it a cyclic test? what film build, what substrate, what type of pretreatment are you looking at? And then, how will it be evaluated for pass fail? So ASTM has several criteria, creep from scribe, a rust grading, a blister grading. And, you may see, a spec come in that says, oh, I need a scribe rating of 7 or better. So you can, that's 2 millimeter creep or less, or a blister rating. Blister rating is similar to the PCI smoothness standard, where there's a physical a physical representation of that you compare your panel to, so you can see. In this case, there's photographs of different levels of blistering, and then you assign a rating of 2 through 10 or 1 through 10 on the size and frequency of the blisters. So when you're looking, when you look at the TDS from your powder supplier, you may see, a corrosion rating of 1,000 hours, but it should also dictate, and it will also dictate what is pass and fail. So in the first example, you have an 1/8" creep, which is a little more than 3 millimeters from the scribe, no blisters, minimal corrosion on the edges. Where in the second example, you have 3,000 hours, and it gives a rating, a blister rating, and a scribe rating. So should be familiar with these as they come in. If this is what your customers are asking for, you'll be able to communicate the performance and the pass-fail requirement, based on that information. And then finally, again, when you look at a TDS, it should dictate, what the parameters were and what the type of panel was tested. So in this example, state film properties were determined using 2.5, 3.5 mils of powder, iron phosphated, non-chrome rinse, pre-treated, 22 gauge, unpolished, cold rolled steel panel. It may say it's an aluminum panel, it may say it's a B1000. But if you're comparing products and how they'll perform, it's important to make sure that you're looking at, apples to apples comparison. And that, yes, concludes the powder part of the section. And so I think that leaves us with about 10 minutes for questions.
Yeah, thank you. There are a couple questions that have come in. The first one is weather roll primer just a standard TDIC?
I'm sorry, can you say that one more time?
Is the weather roll primer just a standard TDIC?
It could be, or it could be a urethane primer. It doesn't have to be a TGIC. It could be a TGIC free. I've seen urethane primers, so there are different weatherable chemistries that primer could be.
Okay. But does the epoxy primer have the same challenges with intercoat adhesion as zinc primer if it's over gelled? Some areas are near full primer cure and others are just gelled.
Yeah, so with most of your epoxy primers, because how tightly they're cross-linked, part of the beauty of them is how durable they are. But if you try and top coat a fully cured epoxy primer or zinc epoxy primer, you may run into delamination with the top coat because there's just nothing for it to grab onto. Again, it's not all epoxy. Some epoxies you can't top coat, but you talk to your powder supplier, they'll be able to let you know if you need to partially cure the base coat before top coating. Usually you do. And you really just need to gel the primer coat, and then you can top coat it and continue to cure the base coat along with the top coat.
Okay. Next question is for Matt. You made a comment along the lines that the media blast will provide better performance than chemical cleaning pretreatment. Is this correct? How about media blast plus chemical cleaning and pretreatment? Also, is there a difference for steel versus aluminum substrates?
So for the sandblasting or shot blasting, it will give you the best surface profile, but at the same time, you can have shots still stick to your part. So we usually recommend a pre-rinse prior to going into your system to kind of knock some of that stuff off, so it'll extend the life of your cleaner. Otherwise, if you don't have the possibility to put a pre-rinse in, we recommend just installing an extra set of bag filters maybe to accommodate for the extra amount of shot that's going to get filtered out as you clean it off. But the combination of mechanical cleaning and chemical cleaning, yes, would work very well.
And is there a difference between steel and aluminum substrate?
Aluminum doesn't normally need to be blasted. It's mostly steel that gets blasted, but yeah, aluminum is a much softer metal, and depending on what technology you're using, it can be a little bit more difficult to pre-treat.
Okay. Do any powder coaters apply pretreatment to blasted hot rolled steel?
I would say yes. I know we have a couple smaller job shops that will see all different types of substrates that will typically do a powder coat.
Okay. And how much better percentage-wise is zinc phosphate better than zirconium on steel in the same conditions?
So typically, like I said, it depends on the spec most likely. But if you're trying to test to failure, you'll see like once you hit about like 2,000 hours of salt spray, you'll start to see separation between zirconium and zinc phosphate.
Okay. Question was they have a incoming total dissolved solids of over 300, and aluminum parts are showing mineral streaks when exiting the dry off, and sometimes they can be seen through the coating. Do you know where these would be caused? Are they caused by the drips from the racks or something else?
It sounds like it would be caused from the drips from the racks. Another thing you might want to check is the chain above it as well. If that's not protected, you might be getting something from the chain actually dripping down. That's something that is kind of a little bit more outside the box, but it might be something worth looking at.
Okay. And sometimes some cold rolled steel sheet metal parts are showing signs of flash rust. What is either causing or what they can do about that?
Depending on what type of pretreatment you're running and how big your stages are, I think this was the question that was emailed in advance, wasn't it?
Yes.
So based on that, I guess the easy recommendation would be to lower your pH in your iron phosphate stage, and you might be able to etch off that rust before it comes out of the pretreatment stage.
All right. And what's the best way to optimize the performance of a 3-stage wash line? You know, iron phosphate, rinse, rinse.
I guess the question I would have is the last rinse a city water rinse or a DI rinse? Because if it's a city water rinse, then I would say at least install a DI halo, and you should see an uptick in performance.
But they'd have to make sure that that's a stainless steel tank then, though, correct?
Yeah, I would well, with a DI water, you recommend a stainless steel tank, but I mean, if you have a regular metal tank, then yeah, you're probably going to run into some problems regardless of if it's city water or DI water, just because it's going to naturally start to corrode a mild steel tank.
Okay. All right. Let's see. Is the flash rust a real problem from adhesion standpoint?
Yes.
What occurs, you know, that they can find on that?
As far as removing flash rust, I mean,
well, if they coat it, what happens? Is it a rusting problem, or is it just a blemish?
With flash rusting, what is probably happening is your parts might be drying off in between stages too fast, and that exposure to the air is what's gonna cause that flash rusting, which, as far as, you know, adhesion issues, it's going to cause adhesion issues down the line, and you're going to see tremendous corrosion performance failures. There's a couple things you can try. There's, depending on if it's an immersion or spray stage, you can add extra risers in a spray system, or in a immersion system have misting halos as they come out of the stages. The main thing is you want to try to keep the part wet from the beginning of your pretreatment system to the end, and you should be able to avoid flash rusting. If you're still seeing it, there are some over-the-side additives that you can put into your rinse tank to try to help address it as well.
Okay. Is there much of a benefit to run an oil skimmer on your alkaline tank?
Depending on the size of your tank. If you have a very large cleaner tank, then yes, it would be beneficial. But if you have a very small tank, it's going to probably take you a lot longer to get a return on investment.
Okay. And we've got time for one last question here. Is there a specially made coating that covers edges better?
There are, and your coating supplier can, should be able to engineer a coating with higher and improved edge coverage. So, if you talk to your powder supplier and ask what they offer in high edge type coatings, they should be able to offer something to you.
All right, Matt, can you go one more screen? There, I think we have the for any questions as we wrap up here. No, go one more.
Okay.
There we go. Got my email up there, and if you have any additional questions, feel free to send them to me at kevin@powdercoating.org. I will pass it along to our speakers, and we will definitely get something back out to you. Otherwise, I want to thank both Matt and Ryan here for putting this together, and thank you all for attending this webinar. Don't forget to check out the Powder Coating Tough magazine online and subscribe today. And please watch for the link of the survey that'll pop right up at the end of this here. Take a few moments to give us your feedback, and have a great day.